In this lesson, we'll begin exploring the idea of limits. First, let's define the limit of a function. We write the LIM for limit with x arrow a, f of x equals L, and say the limit of f of x as x approaches a is equal to L. So the way that we read this notation, LIM is for limit, x arrow a we read as x approaches a of f of x is equal to L. So we say that this is true if we can make the values of f of x as close to L as we want by making x sufficiently close to a but not necessarily equal to a. So in other words, we're investigating what happens to the values of the function f of x as x gets closer and closer to the number a. So it's important to note here that we're not saying what happens when x equals a. We're just interested in figuring out what happens for values of x that are close to a. In fact, the function might not even be defined when x is equal to a, so the quantity f of a may not even be defined, and we'll see examples of that. We're going to investigate how to evaluate limits algebraically, numerically, and graphically. Let's get started with our first example. I want us to look at the limit as x approaches 2 of the function x squared. So we're going to start by investigating this limit numerically. And often, when we're investigating a limit numerically, it can be helpful to create a table of values. So what you can see here, I'm asking what happens to the value of the function x squared as x gets closer to 2. So I've put in x values that are getting closer and closer to 2. And notice that I'm putting in values that are both less than 2 and slightly greater than 2. And again, I'm not interested yet in what happens when x equals 2. I just want to say what happens to the value of x squared as x gets closer to 2. So go ahead and pause the video at this point and go ahead and compute for yourself. So when x is equal to 1.5, what is x squared? You can use your calculator to do this if you want. So this one will be 2.25. So compute the value of x squared for all of these values of x. Go ahead and fill in the table, and then when you're ready, come back and restart the video and I'll fill in all of the values for you. So we get for the values of x squared for these values of x. So here are the numbers we're getting. And what we see is that it looks like, at least numerically, so we have numerical evidence to suggest that as x is getting closer to 2, it seems like the value of the function x squared is getting closer to 4. So from this numerical table of values, as x gets closer to 2, it looks like x squared is getting closer to 4. Okay. So what about graphically? Let's take a look at the graph of the function f of x equals x squared. This is our standard parabola with vertex 0, 0. And so what we see here, as x is getting closer to 2, both from the left, meaning less than 2, and the right, bigger than 2, the values of this function are just getting closer to 4. And algebraically, in this particular function, what we see is that as x gets closer to 2, the values of x squared, well, I can actually plug in 2 squared and see what is happening here. As x gets closer to 2, the values of x squared are just getting closer and closer to 2 squared, which is 4. So in this example, again, we were able to investigate this limit numerically, graphically, and algebraically by investigating what happens to the values of x squared as x gets closer to 2. Now in our next problem, we'll look at a situation where we can't simply plug in and see what happens to the values of our function. So the keys that you want to remember from this video are the definition. So when we write this symbol LIM x arrow a f of x, we're saying the limit of f of x as x approaches a is equal to L, and what that means is that f of x is getting closer and closer to L as x gets closer and closer to a, but not equal to a.